Hello, good morning everyone. In the last class, we are discussing about Poisson's ratio and principle of superposition. What is meant by principle of superposition? If a structure is subjected to several actions simultaneously can be reproduced by adding each actions separately. Adding each action separately. That is what is called as principle of superposition. Okay, and we discussed problems on principle of superposition, and then we discussed about the Poisson's ratio and lateral strain. What is meant by Poisson's ratio? Is nothing but the ratio of lateral strain to the longitudinal strain, and its ratio, the value is in between 0 to 0.5, right? Okay, today we now start with our topic, volumetric strain. Okay, what is meant by volume? Volume having some three dimensions quantity, right? It is a three dimension volumetric. Strain is nothing but again change in dimension to the original dimension. I hope you understand what is volumetric strain. Volume is three dimension quantity of material, and strain is nothing but change in dimension to the original dimension. So volumetric strain is nothing but what? Change in volume divided by original volume. Change in volume by original volume. In the same way, in the last class which we discussed about linear strain and lateral strain, right? Linear strain is nothing but, or longitudinal strain is nothing but what? Change in length divided by original length. Lateral strain is nothing but change in diameter divided by original diameter, or change in thickness divided by original thickness, or change in breadth divided by original breadth. Today we are going to discuss about the volumetric strain. See, this is the volume, consists of three dimension body having length, having breadth, having thickness. Having a length, having breadth, and having thickness. This is three dimension body, and which is subjected to the forces on all the three directions. It undergoes change in volume. It undergoes change in volume. The measure of change in dimension of three dimension body, that is change in volume divided by original volume. Volumetric strain is nothing but change in volume divided by original volume is called as volumetric strain, which is denoted by dV divided by V. V is nothing but original volume. dV or delta V, whatever you call it as, it is change in volume. The change in volume is given by the expression with relates to a volumetric volume, with relates to a volume and Poisson's ratio, which is given by dV is equal to E into 1 minus 2 mu, or 1 minus 2 divided by m into original volume. This is a longitudinal strain into 1 minus 2 mu, or 2 divided by m into V is original volume. So this is the expression for change in volume. You remember, volumetric strain is nothing but change in volume divided by original volume. Okay, ಅರ್ಥ ಆಗ್ತಿದೆಯಾ? ಅಂದ್ರೆ volumetric strain ಅಂದ್ರೆ this is the three dimensional body which is subjected to forces in all the three directions. Okay, this is the length, and this is the breadth, and this is the thickness. Okay, this body is subjected to forces in all the three directions. Okay, then it undergoes change in volume and is having some original volume. So change in volume divided by original volume, which is given by the parameter, is called as volumetric strain. Understand? And the change in volume is given by the expressions longitudinal strain into 1 minus 2 mu into original volume. Okay, into original volume. Right. Next. So one more modulus of elastic constants. It is called as bulk modulus. It is called as what? Bulk modulus. It is again directly relates with change in volume. It is again directly relates with change in volume, which is given by when a body is subject to three mutual perpendicular forces of equal intensity. The ratio between the direct stress and volumetric strain is a constant within the elastic limit, and it is denoted by the letter K, and its unit is Newton per mm square. Remember that when the body subjected to three mutually perpendicular directions, the body is subjected to three mutually perpendicular direction forces of equal intensity, and the ratio between the direct stress to the volumetric strain is a constant when the body which is in within the elastic limit, and this is denoted by the letter K, capital K, and its unit is Newton per mm square. Understand? This is what is called as bulk modulus. The bulk modulus what? Which is directly relates with what? Volumetric strain. Is directly relates with volumetric strain. Okay, so let's we give an expression for this. Bulk modulus is equal to K, which is equal to direct stress divided by volumetric strain. So in the previous slide which we discussed about the volumetric strain, which is nothing but what? Change in volume divided by original volume. Okay, and it is given by the symbol F is the direct stress and EV represents what? Volumetric strain. In the last class which we discussed about E lateral strain is nothing but lateral strain, E lateral. So and E longitudinal is nothing but longitudinal strain. Here EV represents what? It is a volumetric strain. It is a volumetric strain. Okay. Next, what are the elastic constants? What are the elastic constants, and what are the relations between the elastic constant by using Poisson's ratio we need to establish? So first of all we need to discuss about the elastic constants. First one is Young's modulus of elasticity. Again, while discussing about the Poisson's ratio, I gave a brief introductions about the Young's modulus of elasticity. So it's the ratio of stress to strain when which is in elastic region. It is called as a elastic Young's modulus of elastic. Young's modulus of elastic. Okay, when the ratio of stress to strain, which is called as elastic. In the when it is in the elastic region, it is called as Young's modulus of elasticity. See, it is given when you apply the load, it's subject to stressors, and it will undergo deformation. These deformations is within the elastic limit. Then this modulus of ratios is called as Young's modulus of elasticity. Young's modulus of elasticity. Then one more constant we have, which is called as shear modulus. The Young's modulus E is equal to stress by linear strain F by E. Similarly, we have shear modulus. Shear modulus is nothing but the ratio of stress to strain. Again, it is in elastic region. So what stress? Ratio of shear stress to the shear strain, when which is elastic limit and elastic region. This is called as a shear modulus, and it is denoted by C. See, this is the body subject to shear. The top is moving in horizontal direction, and the bottom is subjected to a shear strain and shear stress. So this ratio is known as shear modulus, and which is denoted as C. And shear strain, shear stress, the symbols are tau and phi. Tau and phi. See, remember, shear modulus C is equal to shear stress divided by shear strain, and which is equal to tau by 5. Okay, understand? Next, the previous slide which we discussed, one more elastic constant which is called as bulk modulus, the ratio of direct stress to the volumetric strain. When the material is subjected to 3 mutually perpendicular forces, it undergo deformation, and which is within the elastic limit, the ratio of direct stress to a volumetric strain, which is called as what? Bulk modulus of elasticity, and which is given by the K is equal to direct stress divided by volumetric strain F by EB. Okay, these are the what? Modulus of elasticity and shear modulus and Young's modulus and bulk modulus. Okay, Young's modulus of elasticity or modulus of elasticity is nothing but same. Shear modulus or rigidity modulus is same, and bulk modulus is nothing but K. Okay, there will be different sign convention depending on the users, but we are commonly using it as E, C, and K. E, C, and K. E for Young's modulus of elasticity, C for shear modulus, and K for bulk modulus. So don't confuse with the symbols. Remember, E is nothing but Young's modulus, C is nothing but shear modulus, K is nothing but bulk modulus. Okay, bulk modulus. So Young's modulus is represents the longitudinal strains and linear strains, okay, and shear modulus represents it's a shear strain subject to shear stress, shear stresses, and bulk modulus is nothing but direct stress divided by volumetric strain. It's a volume changes. Okay, so don't confuse with these symbols. Again, these symbols are represents the different elastic constant. We are using generally these symbols for these slides or this course. Okay, now one relations we need to establish between the elastic constants, these relations are called as ECK relations. These relations are called as what? ECK relations. What is meant by E? Young's modulus of elasticity, and C shear modulus, and K is bulk modulus. So these constants are always within the elastic limits, then these are called as elastic constants, and it is E is nothing but Young's modulus, she is nothing but shear modulus or modulus of rigidity, and K is nothing but bulk modulus. Okay, and one more we discussed in the last class about the Poisson's ratio, which is called as mu or 1 by m. Okay, which is represented. Sorry. They are known as elastic constants. They are known as what? Elastic constants. These constants have a definite relations within themselves. ಅಂದ್ರೆ ಅವೆಲ್ಲ ಕೂಡ ಸೇರಿ ಒಂದು ರಿಲೇಷನ್ಸ್ ಫಾರ್ಮೇಷನ್ಸ್ ಆಗಿದೆ. ಅವೆಲ್ಲ ಕೂಡ ಏನಾಗಿದೆ? ವಿತಿನ್ ದಿ ಎಲಾಸ್ಟಿಕ್ ಲಿಮಿಟ್ ಆಗಿದೆ. Within the elastic limit, these relationships existing themselves is known as elastic relationships or ECK relations. Okay, let's see what are the relations which they have. Okay, so first one, the relations between Young's modulus of elasticity and modulus of rigidity or shear modulus. Okay, what is the relations? Let's see. E is equal to 2c into 1 plus mu, where E is what? Young's modulus of elasticity, 2 into c is a shear modulus into 1 plus mu. Mu is nothing but what? Poisson's ratio. So this is the relations between elastic modulus of elasticity and shear modulus. With the help of, we are establishing a relation, that is Poisson's ratio. So that's why this relations is called as between the E and C. Okay, if you know elastic modulus, if you know Poisson's ratio, we can able to find out shear modulus. If you know shear modulus and Poisson's ratio, we can able to find out elastic modulus. And these three parameters are again within the elastic limit, within the elastic limit. Next, the relation between E and K, that is elasticity, Young's modulus of elasticity, and bulk modulus. Uh, Bulk modulus, right? So elastic modulus of Young's modulus of elasticity and bulk modulus of elasticity relation is given by E is equal to 3k into 1 minus 2 mu. E is equal to 3k into 1 minus 2 mu. When we know Young's modulus of elasticity and Poisson's ratio, we can able to find out bulk modulus. Or we know bulk modulus and Poisson's ratio, we can able to find out Young's modulus of elasticity. So So these relations which gives what parameter, if we know linear strain and volumetric strain, you can able to find out when we subject it to a direct stresses, we can able to find out Poisson's ratio. Similarly, if we subject it to a direct stress and shear stress, we can able to find out Poisson's ratio. Or if we know Poisson's ratio and the parameter of lateral strains and the stresses, we can able to find out shear stresses. So these are related to each other. When the material is subjected to a stress, it undergo deformation, that is measured by the parameter having the constant relations, which is known as a Poisson's ratio. Then we can able to find out alternative parameters like shear modulus and bulk modulus. So then what is the relation between three among them? ECK. 3 ck, which is given by E is equal to 9 kc divided by 3k plus c. 3k plus c. Okay, this is given by the relation 3k plus c. 3k plus c. Okay, these are the three relations, the very most relations in order to find the different parameter within them. So we are using these three relations. Okay, we are using these three relations. Next, I have a problem on these relations and bulk modulus, and it is volumetric strain and these relations. Okay, I'll read out the question. Please read the questions very carefully and write the data. A mild steel bar 28 mm in diameter was subjected to an axial pull of 60 kN. The measured extension for a gauge length of 200 mm was 0.09 mm and change in dia was 0.00375 mm. Calculate Poisson's ratio, Young's modulus and shear modulus. Three parameters we need to find out. Okay, three parameters we need to find out. First, write the given data. What are they given? Diameter of the bar is given. Steel bar. My steel bar is 28 mm. Okay, it is subjected to an axial pull. Again, it is 60 kilonewton. Right? 60 kilonewton is nothing but 60,000 newton. And L is 200 mm. The length was 200 mm. The gauge extension for a gauge length, measured extension for a gauge length 200 mm was 0. Delta L is 0.09 mm. And diameter was changing was delta phi is 0.00375 mm. Change in length is given, change in diameter is given, original diameter is given, original length is given, and the load applied is given. Then we can able to find out load by area. By knowing the diameter, we can able to find out the area. A is equal to pi d square by 4. So load by area, which gives stress. We can able to find out stress, force by area. Then strain, longitudinal strain is equal to change in length divided by original length. Then it gives longitudinal strain. Then can also find out lateral strain, which is equal to what? Which is equal to what? Lateral strain is nothing but change in diameter divided by original diameter. That is also given, which gives lateral strain. We can able to find out Poisson's ratio. Mu is equal to lateral strain divided by longitudinal strain. We also know mu. We can able to find the Young's modulus of elasticity. E is equal to stress by longitudinal strain. Stress is already, we can find that by using this given data. Okay, let's we start. So one thing, when you are solving the problems, first of all you need to read the questions very carefully and write the given data, and even write the what are the things you should find, you should need to find. Okay, that is mu, E and C. Mu, E and C. Okay, first E lateral, that is change in diameter divided by original diameter, which is equal to how much? 0.0001339. E lateral is known. It is by using given data we are finding that. No more alterations is required to find the lateral strain and longitudinal strain. Okay, linear strain or longitudinal strain delta L by L is equal to 0.09 divided by 20 is equal to 0.00045. Okay, next mu, Poisson's ratio. So lateral dimensions having a constant relations with ratios of longitudinal strain, that is given mu is equal to E lateral divided by E longitudinal, which is equal to 0.2978. It's a unitless quantity, dimensionless quantity. Okay, next what we need to find out: stress, load by area. Load is given 60 kilonewton and area we can able to find out 97.498 newton per mm square. Next mu is equal to E lateral by E longitudinal, which is known, and E is equal to 2c into 1 plus mu, 2c into 1 plus mu. So stress is we have calculated already, and mu and E is can able to calculate. Okay, and C you can able to calculate here. Okay, C by knowing E and everything. Shear modulus is able to calculate. Shear modulus E is able to calculate. Now move on to next problem. Before you start with any problems or numericals, please try to read out the questions once. I will read out. A bronze specimen has a modulus of elasticity 1.2 into 10 to the power of 5 Newton per mm square, and modulus of rigidity of how much? 0.47 into 10 to the power of 5 Newton per mm square. Find the Poisson's ratio. Very simple problem. A bronze material, the two elastic constants are given. They are need to ask find what Poisson's ratio. We have the relations between Young's modulus of elasticity, shear modulus or modulus of rigidity, and Poisson's ratio is equal to what? E is equal to 2c into 1 plus 2 mu. E is equal to c into c into 1 plus mu. Okay, 2c into 1 plus mu. Right? Write the given data C, E, and we need to find out mu, Poisson's ratio. We have relation E is equal to 2C into 1 plus mu. So substitute everything. E 1.2 into 10 to the power of 5, 2 into 0.47 into 10 to the power of 5 into 1 plus mu. You can able to find out mu by using these relations, and you should have a calculator, scientific calculator, trying to work out the number of multiples we have in denominators, we are having additions, subtractions, with maintain the brackets and able to find out the right answer. Please try to practice how to use the calculator, okay. So mu is equal to how much? 0.276, 0.276, right? This is the answer we have for a bronze material, and they are given elastic constants like Young's modulus of elasticity and rigidity modulus. Next problem. For a given material, Young's modulus is 1 into 10 to the power of 5 Newton per mm square, and modulus of rigidity is 0.4 into 10 to the power of 5 Newton per mm square. They are given both here also, shear modulus and Young's modulus. They ask to find the what? Bulk modulus and lateral contractions of the round bar of 50 mm diameter, and which is 2.5 meter long when stretched by 2.5 mm. When stretched by 2.5, diameter is given. Original diameter is given. Length is given. And delta L, change in length, is also given. They are asked you to find the what is called as contraction of a round bar, lateral contraction. They ask you to find the change in diameter of the bar. Okay, it's very easy. They have given these three, then we can able to find out. Okay, write the given data. E is given, C is given, D diameter is given, length is given, delta L is given. You need to find out K. You need to find out D, delta D. Now the next you can able to find out Okay, first you find out mu by knowing E and C. Yes, this is substitute the values E and C here, and mu is equal to how much? It is 0.25. When we know mu, we have change in length and original length. Again here, you can able to find out bulk modulus also by a relation between Ek and mu. What is the value of bulk modulus? 0.66 into 10 to the power of 5 Newton per mm square. Next, only thing you have to find out is change in diameter. Change in diameter, right? Linear strain is equal to delta L by L. You can have the relations and find out it is 0.001. Next, you need to find out change in diameter. For that, we have relations. Mu is equal to what? This Poisson's ratio is equal to lateral strain divided by linear strain. Lateral strain divided by linear strain. So then lateral strain is equal to longitudinal strain into Poisson's ratio. Find out that 0.00025 lateral. So again E lateral is equal to what? Change in diameter divided by original diameter. Correct? Change in diameter divided by original diameter. You need to find out change in diameter. That is lateral contraction of the round bar. You have to find out. So how much it is? See, the diameter of the bar is going to be decreased by how much? 0.0125 mm. 0.0125 mm. Okay, understand? Okay, this is how to find out the change in diameter. Change in diameter. Okay. Next, one more problem. Show that modulus of rigidity is 2 by 5 times E when Poisson's ratio is 1 by 4. Very good. Show that modulus of rigidity is 2 by 5 times E. That is, E is nothing but Young's modulus of elasticity when Poisson's ratio is 1 by 4. 1 by 4. Okay. We have relation between E, C and mu. Correct? They have given modulus of rigidity in terms of Young's modulus of elasticity, and they have given Poisson's ratio. We need to establish the relation between E and C. Yeah, C. Okay, right. Okay, mu is 1 by 4, which is equal to 0.25. E is equal to 2C into 1 plus mu. We need to show C is equal to 2 by 5 times mu, right? Correct. Next, 1 by 4. E is equal to 2C into 1 plus 1 by 4. So do cross multiplication and add numerator and kept the denominator separately. So 5 by 4. So which is equal to 5 by 2. So again do cross multiplication. C becomes 2 by 5 times E. So this is the final answer. Very easy. So simple questions, you need to understand what they have given and what they need to ask you to find. Okay. Next problem. A copper wire of 40 mm in diameter is subjected to a pull of 80 kN, 80,000 Newton. It reduces its diameter by 0.00775 mm. The modulus of rigidity of material is 0.4 into 10 to the power of 5 Newton per mm square. Find the Poisson's ratio and the Young's modulus. So in the previous problem, second problem, we find bulk modulus. Right? They have given everything. Here they ask to find Young's modulus and Poisson's ratio. Very good. So you can write the given data. D is given, load applied is given, diameter change in diameter is given, shear modulus is given, and then they ask you to find the Poisson's ratio and Young's modulus of elasticity. Okay, first find the stress load by area by knowing the diameter. Can able to find out the area, and the load is given 80 kilonewton, 80 into 10 to the power of 3. We are keeping all the units in Newton per mm square. Newton per mm square. Next, E lateral is equal to change in diameter divided by original diameter. Original diameter and change in diameter both are given. E lateral you can able to find out. Okay, so then what you have to find out here? Young's modulus E is equal to stress by strain. So E is equal to F by E. So this is the first one. As per our question we need to find out. This is the one relation you kept in your mind. Next, mu is equal to E lateral divided by E longitudinal. So E longitudinal is equal to E lateral by mu. Next, this is the second relation we have. In order to generate, we need to find out what? Mu we need to find out, and Young's modulus of elasticity we need to find out. So next, combination of 1 and 2, we established the relation mu is equal to E lateral by E longitudinal. Next, F by E is equal to E lateral by mu. E by mu is equal to F by E lateral. So E by mu we can able to contain, because stress is known, E lateral is known. It is E by mu is equal to 30020.7. This is third relations we have. Again we need to find out E and mu here. We know ratios of E mu. Okay, next comes to a relation E is equal to 2c into 1 plus mu. So E by mu is equal to, we know already. So C is also known, mu is unknown, and E is unknown here. E by mu is equal to known, right? Mu is equal to 337. Substitute the E by mu, and mu is unknown, 2C is known. So find out mu. Mu is equal to 0.32. Substitute 0.32 in these relations, you will get E. So E is equal to 1.05 into 10 to the power of 5 Newton per millimeter square. 10 to the power of 5 millimeter square, correct? E is equal to how much? E is equal to 1.5 into 10 to the 1.05 into 10 to the power of 5 Newton per millimeter square. Okay, so this is the relations which we are having. Okay, this is about the problems on bulk modulus, shear modulus, and Young's modulus of elasticity, and which relates with lateral strain, longitudinal strain, and also Poisson's ratio. When these materials of constants are within the elastic limit, we can able to find the any parameters and the subjected to loads and stresses. Okay, loads and stresses. Okay, now we discussed about a few multiple choice questions. Among them, first question is, so Young's modulus may be defined as the ratio of dash. This is the question, and the choices are linear stress to linear strain. First choice. Second choice, linear stress to linear strain. Third choice, lateral stress to linear strain. Fourth choice, shear stress to shear strain. So Young's modulus may be defined as the ratio of what? Linear stress to the linear strain. Linear stress to the linear strain. Okay, remember. So this is the answer. Linear stress to linear strain. Okay, move on to next question. The ratio of the lateral strain to the linear strain is called as what? The ratio of the lateral strain to the linear strain is called as what? Okay, the choices are elasticity modulus, rigidity modulus, bulk modulus, and Poisson's ratio. So which parameter which relates to a lateral strain and linear strain? It is Poisson's ratio. Next, third question, the ratio of change in volume to the original volume, which is called as linear strain, choice 1, lateral strain, choice 2, volumetric strain, choice 3, Poisson's ratio. Change in volume divided by original volume is the change in dimension, the parameter which reference to strain, and it's a 3-directional change in deformation. So that's why it is called as volumetric strain. That's why it's called as what? Volumetric strain. Okay. Next, modulus of rigidity is defined as the ratio of what? What is modulus of rigidity? It is a shear modulus, right? So choices are tensile stress to tensile strain, compressive stress to compressive strain, longitudinal stress to longitudinal strain, and shear stress to shear strain. It is a shear modulus. Already I told you rigidity modulus is nothing but then obviously it is the ratio of shear stress to shear strain. This is the answer. Okay, these are the few MCQs which relates to this topic. You go through the study material we have given, and if you have any doubts you can clarify, get it clarified. Okay, so please remember, uh, always write the formula and use the calculator, and remember the relations between the modulus of elastic constants. So and try to analyze the problem carefully. Thank you.